Hello everyone, and welcome to the presentation of our paper VDGR, Boosting Visual Dialogue with Cascaded Spatial-Temporal Multi-Modal Graphs. This is a joint work with colleagues Lei Shi and Andreas at the University of Stuttgart. So without any further ado, let's just dive into it. For those of you who are not familiar with visual dialogue, the task consists in engaging in a dialogue with a model on some visual grounding. The model needs to reason about an image and a dialogue history in order to answer the question at hand. Previous works mainly focused on two classes of models. Some leverage transformer-based models since they can benefit from pre-training on similar tasks and directly fine-tune them on visual dialogue. Although transformers are efficient in learning the global inter-model context, they generally fail at learning the fine-grained local intra-model features. The other class focus on GNN-based models. Although GNNs lack the ability to learn global inter-model context like transformers, they excel at learning local fine-grained features. To benefit from the complementary strength of both classes of models, we introduce VDGR, a novel visual dialogue model that integrates GNNs into language models. As shown in the figure, each VDGR layer alternates between multimodal GNNs and a BERT layer. The former learn fine-grained local structures within modalities, and the latter focus on global context across modalities. To mitigate the lack of global context within GNNs, we propose to propagate information between modalities using hub nodes. Finally, we use the GNN features to enhance the hidden states of the subsequent BERT layer. Now let us dive deeper into our model. First, it takes an image, a question, and a dialogue as inputs and constructs suitable multimodal graphs using spatial relations between objects in the image, dependency relations between words in the question, and coreference relations between rounds in the dialogue. We invite technically inclined readers to check out our full paper for more details. We then apply our novel GNN integration technique. Each GNN inherits the node features from the previous BERT layer. Then, it updates them based on its structure before propagating its information to the next GNN via hub nodes. Finally, we use GNN node features to augment the hidden states of the next BERT layer. Finally, the hidden state of the last VDGR layer are fed into different loss heads. In graph edge masking, we propose to learn masked edges based on the node features it connects. This training task significantly boosted the performance of our model, as we will see later. Finally, we learn to rank a set of candidate answers using similarity measures with the ground truth answer. For training, we adopted a two-stage scheme. We first learn a warm-up task composed of the mask language, mask region, and masked edge modeling losses. This first training stage should prevent the model from having well-trained BERT layers and not as well-trained GNNs. Then, in the second stage, we train with the established visual dialogue loss by jointly optimizing the mask language and region modeling losses and the next sentence prediction loss. We first evaluated our model on the VisPro and VisDialConv dataset. As seen in the first section of the table, VDGR managed to significantly outperform all previous models across all evaluation metrics on VisPro. We also see a similar behavior on VisDialConv. VDGR not only outperforms the MCA baselines, but also the more recent student model. Then, we assessed the performance of our model on VisDial v09. As can be seen from the table, VDGR outperforms all previous models across all evaluation metrics by a significant margin. Specifically, it lifted the performance of VisDial BERT and VD-BERT by over 2.5 absolute points on MRR and RECOLLAT-1. Then, we evaluated on the more recent VisDial v10 dataset. On the validation split, VDGR achieves new state-of-the-art results across 5 metrics out of 6 and ranks second on NDCG after the student model. On the test split, our model managed to achieve new state-of-the-art results on 3 metrics, that is RECOLLAT-5, RECOLLAT-10, and mean. As it is standard practice for visual dialogue, we fine-tuned our model on dense annotations to improve the NDCG score, which is the most important metric of the dataset. As can be seen from the table, VDGR managed to achieve a new state-of-the-art NDCG score of 75.95 while keeping high sparse scores. Finally, our ensemble model managed to further increase the NDCG score to 76.43, thereby setting a new state-of-the-art results on the task. Finally, we show some interesting results from our ablation study. First, we want to emphasize the role of the two-stage training, as training without the warm-up task of graph edge masking led to drop in performance across all evaluation metrics. Then, we trained without sharing the weights of the multimodal graphs across the VDGR layers. Since we kept the graph structures in every VDGR layer constant, this version did not perform as well as our best model with GNN weight sharing. Finally, we updated the information propagation through hub nodes between the multimodal graphs. Similarly, this version underperformed our best model, which underlines the efficiency of our novel approach. So to conclude, in this paper, we proposed VDGR, a novel visual dialogue model that alternates between multimodal GNNs and BERT layers. Each GNN augments the hidden states of the following BERT layer after locally propagating information through hub nodes. Through extensive evaluations, we show that our model achieves new state-of-the-art results on 4 different visual dialogue datasets. By this, we reach the end of our presentation. Please consider checking our paper by scanning the QR code. Thank you very much for listening.